Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully you guys are doing well. Let's jump into it. We are continuing our excursion into interest, and we're kind of in the middle of that section, so no more intros or pleasantries. Let's just actually jump into it. We left off last time just talking about some situations where you'll see the different kinds of interest in the real world. We did some examples with simple and compound interest. We're going to do some more examples. I had them here in the notes. I don't know if you guys saw them, but we're going to go through these guys today. Maybe even some more. Lots planned today. Let's see how far we get. But I actually want to go over simple and compound for a little bit, and then get into the other one, compounded continuously. So we will begin with the interest smackdown. So what we're going to do is we're going to just look at some numbers to just see how different these guys can get, because the examples that we did last time went up to like a year, and there was like only like $4 difference between the two of them. So I thought that I would, go out a little bit longer, 5 years, 10 years. I thought I would do like a 20% APR, which is like what a credit card is, and to just kind of see how the growth would be different over a longer time span. So let's actually do that. We are going to fill out this table. So let's say, yeah, I'm in blue. Someone's trying to get in here. So let's look at time, simple interest, and compounded daily. So we're going to fill out this table. Yeah, I think I only had 2 rows. We already did the year one for 1 year down the road. Let's look at 5 years down the road and 10 years down the road. The 1 year down the road didn't look that different, right? We did that and it was like $9 or $4 or something like that, less than $10. So we'll fill out this table via calculations. Below the table. Okay, so I'm going to do the calculations underneath so you can see where the numbers come from, or I guess to be more specific, you guys are going to do the calculations underneath. I need to make sure that you remember the formulas, you remember how to use them, you know how to use your calculator and things of that sort. So let's jump into it. So if I wanted to do, let's say, the simple interest calculations, how would I do it for the 5 year? What is the formula? What do I plug in?
The formula for simple interest is A equals P parentheses 1 plus RT.
Yep, that looks fine. And so here, look at this. Our P is 1,000. The R is 20%, which is 0.2. And T is, we're looking at 5 years here. So P, 1,000. R, 0.2. T equals 5. And we're going to do T equals 10. So here we have 1,000. 1 plus 0.2 times 5. And what does that give us?
2,000.
2,000, right? which actually makes sense. It doubles, right? Why does it double? You're getting 20, they're charging you 20% interest. 20% is 1/5, and we've actually gone 5 years into the future. So you get 1/5, 1/5, 1/5, 5 times, you get a whole. And so you actually have to pay back 100% on top of what you borrowed, right? Very steep, but then again, 20% interest is also very steep. It's very out of the ordinary to get a 20% interest. I feel like the only people who do that are credit cards. Like it's very rare for you to have interest rate that steep. But yeah, interest rate this steep, even with simple interest, you'll double what you owe within like 5 years, 10 years. We'd use the same formula. Now it's times 10. Now what you expect is, again, they're charging you 1/5, 1/5, 1/5. You should add another 1,000. So that should be 3,000, right? And remember, simple interest is always charging on the principal. So they're always taking that percentage based on the original 1,000, right? So you'll actually gain another 100% on the original 1,000, which is another 1,000. So now you have 3,000, right? So you take a simple interest loan at 20%, don't make any payments. After 5 years, it'll double. After 10 years, it'll add another 100%, which is not, it would triple from the original, not quite double from the 5-year mark. Okay, so that would be here. So after 5 years, you would owe 2,000 here and 3,000 here. Now, let's see what a credit card would be like. Let's say you make no payments for that long, which shouldn't happen. So let's do the compounded daily. P equals 1,000, R equals 0.2, T equals 5 and 10, and N equals 365 daily. Okay, so let's look at the 5 years. What's the formula for compound interest?
The period multiplied by 1 plus R over N to the NT.
Right. Principal, right? And so we have here 1,000, 1 plus 0.2 over 365 times 365 times 5. We're going to have a similar thing for the 10 years. So you guys can just do both of these at the same time. Tell me what the answers are. Five years.
2,717.54.
Okay. And for this one?
$7,385.009 or 0.01.
Yeah, those numbers sound right. So this is around 2,717. This one is around 7,385. Now, hopefully you start to see some difference, right? So last time we were like, oh, it's just like $4. Okay, so after 5 years, they can get $700 extra from you. And it's not even joking. Look how much it grows after the 10-year mark. It grows by even more than it grew by originally. Right? So that's an extra like 4,300. Like it's no joke, right? So this is the kind of thing that I really want to hit home, is the power of compound interest. And it's not a power that you kind of notice in the beginning. After 1 year, it's like, what? Okay, they got 4, 7, 10 extra dollars for me. No big deal. If you let it go for a long time and you're in a particularly unfavorable situation, as you would be with the average credit card, it can get out of hand quite spectacularly. So just wanted to make sure that that was kind of understood. It may have seemed underwhelming to you last time when I was hyping up compound interest, and then it's like for $4, that's all his hype. That's what his hype was about. I wanted you to know the hype is real. There is a very good reason to be very wary of the kind of interest you're being charged and keeping on top of it when it's being compounded. So now let's actually talk about the other guy, the third guy. We're going to talk about continually compound interest. Continuously, compounded continuously. This is when interest, when compound interest is compounded an infinite number of times per year. As I mentioned, we can't actually do this in reality. So this is for theoretical purposes usually. You can get a lot out of knowing what the worst case scenario would be for a loan, or what the best case scenario would be. And we can derive a lot of other formulas from knowing things like this. But no, we can't actually computationally do this. However, we can actually get a formula for it so that we can artificially do it if we ever so intended. So remember, this was the question that Euler was thinking about when he invented the number E. I mentioned that a few classes ago. And remember what he found. He found that basically, if you have $1 and you're charging 100% interest, and you're compounding it an infinite number of times per year over 1 year. So here it's like, n is going off to infinity, right? So he just kept making the n larger and larger and larger and larger and larger. And what he noticed was that it was approaching some number. This number has been since dubbed the name E, right? Which is 2.718 right? Non-repeating decimal, right? So that we know from Euler, right? So we know that this expression 1/1 to the n will get close to the number E as n goes off to infinity, right? So theoretically, we know this, okay? So now we're going to apply that to the old compound interest formula. What does this mean for the compound interest formula? So what would happen to A equals P 1 plus R over N to the NT if N goes off to infinity? Right? What would that even mean? To let you see it a little bit clearer, we can do a change of variable. I'm going to set x to be equal to the reciprocal of the interest part. So that means I can think of n as x times r. And as r is going to be a fixed interest rate, we're just going to think it's some percentage that's given. But x I'm thinking of as a variable because n is a variable. N is going to be moving for us. And so notice that I can let n get bigger by letting x get bigger. As x goes to infinity, then n goes to infinity. So I can actually control how big n gets by controlling how big x gets. Now, at first, you might not see why do I need a new variable, but it's really just for you to see the pattern. So what would happen here? Notice that if I try to plug in x into this equation, this part would be 1 over x because it's the reciprocal. And I can replace my n with x times r times t, right? And so now, let my x go off to infinity. It's the same as letting n go off to infinity. From the laws of exponents, I can write this as that. I can factor off the powers. And so now you might ask the question, well, what happens to this guy as x goes to infinity? Well, I told you above that this guy goes to e as n goes to infinity, and n is just some variable that's blowing up. Here, notice that you're in the same situation. X is some variable that's blowing up, and it looks exactly like that expression. So that actually becomes e. So what I have is p times e raised to the RT. And that's the compounded continuously formula. So we get PE to the RT, that's the PERT formula. This is the compounded continuously formula. Now, E is also a number that's in your calculator. You need to make sure that you know how to find it because you will be needing to use it, but that's going to be the formula, the PERT formula. Those of you taking calculus and you've done things like exponential growth and decay, the formula should seem familiar to you, but otherwise you should just know that that's the formula. So P e to the RT, that's how it looks compounded continuously. So now let's actually make sure we know how to use it. Did I do another one? I don't know if I actually wrote that down. Yes. So I just want you guys to do the calculations for these 3 time spans so we can even compare it to these numbers. So we already know what these guys look at after a year. Well, we're not doing 20%. I'm doing the 9.5. So you have to compare these numbers to like the ones from last class. Suppose we borrow $1,000 again, 9.5% interest rate, but now it's compounded continuously. No payments are made in the interim. How much would be owed after 1 year, 5 years, 10 years? So let's actually check that out. So A, P equals 1,000. 95.095. T equals 1. And it's going off to infinity. But that means that we use the PERT formula. So this means our A is equal to P e to the RT. And so this is going to be 1,000 e to the 0.095 times 1. What is that? Make sure you can calculate that. Did we do 5 years last time? I don't think we did 5 and 10 years for the 9.5% interest rate, but you can do it on your own and compare them. What do you get for this one?
$1,099.
And how many cents?
66 cents.
Yeah, that sounds about right. Yeah. So instead of gaining like, again, it's not that much after 1 year. Last time, how much did we get from compounding? 9.5. That's simple interest. After 1 year was 95. Now we're up to 99. We did compound interest. After 1 year, you get 98. In order to approach like the 99 level mark, of course, we difference of 1 cent, we literally have to compound every day. So again, even though we're quite different, you can actually approach a situation where it's almost like you're compounding continuously if you're compounding daily. But of course, the difference grows as you move out. Yeah, so that's that. B. We're going to do the same thing. Here t equals 5. N is going off to infinity. Again, I'd write down the formula every time until you completely remember it. So this is going to be, someone's trying to get in here. So this is going to be 1000 e to the 0.095 times 5. I did this, I got 1608.01. So you can check that on your own. Make sure that I did that correctly. In part C, we're doing 10 years. This is 1000. R equals 0.095. T equals 10. N goes off to infinity. This implies that A equals PE to the RT. And for that, I got 2,500, 8,571. And for fun, you guys know how to do it now. You can do the simple interest calculation and the compound interest calculations for the same time periods and the same interest rate, and you can compare them. You can see how they start to diverge. So this one after a year is actually not much different from compounding daily. But as you go out 5 years, 10 years, you'll start to see the gap widen there. Yeah, so that's that. Hopefully that's understood, but that's it. For compounding continuously, like I said, that's the third kind of interest rate, but it's kind of like compound interest on steroids. That's basically what it is, but it's enough to have its own category because the formula changes. So there are 3 major types of interest, but really it's kind of like 2, and then one of them is refined more for this other situation. Here's something that might be an issue though. Let's say you want to do a comparison. I want you to see the potential issues that can arise here. So let's say instead of borrowing, we want to invest money somewhere, right? So we go to someone to invest our money and they make us certain promises or guarantees. So one person says, you know what, you invest your $1,000 with me. I can promise you that I can get you a 3.93% APR return compounded monthly. Someone else says 3.97 APR compounded quarterly. Someone else says 3.94 compounded continuously. Someone says 3.96 compounded daily, right? So one of these are the best, right? How do you choose where to put your money when you have all these different interest rates and they're actually being compounded differently? There are different kind of structures to go along with them. One thing you could do is, yes, you can do the compound interest formula for all of these, but of course that's going to kind of be quite annoying to actually have to do a calculation every time you talk to somebody. So there is another way. And this is going to bring up something that is you should have heard before, but now hopefully you're going to understand the need for such a thing. And you might have heard it and you might be wondering what's the difference between that thing and APR. And that thing that I'm talking about is APY. So sometimes you see that. So to best deal with questions like above, we use instead something called the effective interest rate. Or more commonly, it's called the annual percentage yield. And that is abbreviated APY. Okay. Now, what does this actually mean? It tells you effectively what interest rate you're getting. And how does it do that? Is it will convert whatever interest scenario you're in to a simple interest scenario. So it kind of transforms your APR, how much percent you get per year, into a simple interest situation where your mind works better for that. You'll be able to compare very easily because you change to kind of a linear scenario. But it only works over a year. Of course, if there are several years, it gets compounded per year. But you can know within 1 year who's going to be better. So this helps us compare APRs by converting them to simple interest APRs. So how does it do this? Well, it kind of literally does that. It sets, so set, t equals 1, right? So we're just looking at 1 year, and you might be looking at something that looks like this. To the n times t. So this is the compound situation. I here just stands for interest, which is R over N. So this is the compounded situation and the simple interest situation. So the simple interest situation would look like this guy, P times 1 plus R times T. And basically what the idea is, we set these equal to each other, right? So we force equality here. Okay. What would it look like for this compound interest scenario to be a simple interest scenario? How would that affect things? And I want to use a different variable here to not mix up. So this would be the equivalent simple interest rate. is the original compound interest rate. Okay. Now, if you have this equation, what you can do is you can divide both sides by P. So you have 1 plus I raised to the n equals 1 plus big R. And what you can do is you can solve for big R. So your big R would be equal to 1 plus I to the n minus 1. And so this would mean your big R would be equal to 1 plus R over n to the n minus 1. So this leads to how we compute APY. APY is computed by taking this expression. And this is called the APY formula. And essentially what this does is it converts your compound interest scenario into a simple interest scenario. So what does that mean? If we go back and kind of look at this, so we saw that simple interest, for example, in one situation, you would gain $95 in this scenario, right? Which is 9.5% of the original amount, right? Which is what they quoted to you, 9.5%. However, in the compound interest scenario, we gain 99, which is not 9.5%. That's actually 9.9%. So even though they stated 9.5, effectively what happened to you was a 9.9, right? So this is what's called the nominal interest rate. When they say APR, that's the interest rate in name. What effectively happens to you can be different. In fact, when it's compounded, what's happening to you is going to be greater. So they will tell you 9.5, but really what's happening after the first year is 9.9. And then this grows over the year, right? So this leads to the idea of the effective interest rate, right? What are you really charging me? Yeah, you say 9.5 compounded, but what does that really mean? In this scenario, it really means 9.9, right? So effectively, it's a 9.9, even though they said 9.5. So that's the idea. APY is trying to get to that effective rate. And this is how you can do it, right? So if you want to know, someone states a rate in compound interest, and you want to know, what does that really mean? What you can do is you can convert it to APY. And that will tell you what the actual interest rate over the year is going to be, right? So that pretty much translates your compound situation into a simple interest situation. And you figure out what would be the simple interest rate where, you know, when everyone tells you a simple interest rate, that's what it is. You know exactly how much you're being charged. Okay. So that leads you to APY, right? So what I just said, I wrote something down to say that same thing. I don't know. Do I want to write it down again? So maybe I'll actually put it in words in case someone wasn't listening. Why is this important? Say you borrowed $1,000 at 9.5% APR compounded quarterly. We saw you would owe 10. We looked at this last time and I wrote it down. 1098.44 at the end of 1 year. This means effectively, the interest rate was not 9.5. Right? That's not what it was. That's what they quoted, but rather 9.8. Okay. And this is another reason why people kind of get in trouble with compound interest, because the numbers that you're reading aren't really the numbers that are affecting you. Once you start throwing in compound interest, you might be telling yourself at the end of the year it's 9.5%, but effectively it actually is more, right? You're actually growing faster, and then this adds over time on you, right? So sometimes instead of looking at the APR, what you can do is look at APYs, and there are going to be situations where APYs are used instead of APRs, and I'm going to talk about why that is. It's actually a business decision why someone would use an APY versus an APR. So this guy here, APY would tell you this. And how do I know my APY would tell me that? Well, I can actually do the formula for you right now. What is the APY for 1 plus 0.95% interest rate compounded quarterly? Right? If you actually do those calculations, can someone actually do that so you know I'm not messing with you? Do this calculation here and tell me what you get.
O dot 0.098.
98 what? How many? Do you have more decimal places?
4, 3, 4.
4, 3 what?
4, 3, 8.
Okay, so if I rounded it, it would be 9844, right? That's exactly the number that's right there, that we did a different calculation and got to that number, which means if someone told you, hey, I'm going to charge you 9.5% interest rate compounded quarterly, what you could do is go to the side and do this calculation to see what they're really charging you, right? So he says 9.5, but really it's 9.8, right? And again, the 0.5 and the 0.8 does not seem like a big deal in the short term. It's just another 0.3%. I mean, how much damage can that do? A lot of damage when it's being compounded year over year. Okay, so in this context, we call the 9.5% APR the nominal interest rate. Right? Nominal means only in name, but the reality may be different. And the APY, the effective interest rate. Right? So they'll tell you one thing in name, but effectively in reality, something else is happening. Okay, so that's why APY is important. And now you can see when you're in a situation like this, where people are quoting a bunch of APRs to you, one of the best ways to actually figure out who is the better one to go with is to actually just compute the APYs. Now, the APYs, if you compute the APYs for everybody, that tells you what each person is really giving you. And then you can make the comparison easy peasy. You don't have to go through in the calculator and plug in each of these calculations, but they would tell you the APY, or you can request the APY and have them tell you the APY instead. So you would say, don't tell me the APR, tell me the APY. So back to this question. And I made you guys calculate this one, so I won't make you guys calculate the other ones. I did the calculations previously, so I'll just write down what I got, and you guys can check afterwards. What you can do now is for each of these, what I can do is I can instead calculate the APY with that same calculation that I gave you earlier. And here's what I actually got. So that 3.93 compounded monthly, effectively, it's actually 4.002%, right? So what you should expect to see on your money after 1 year with this person is an additional $4, right? And 002 cents, right? So the 3.97 compounded quarterly, what that really is 4.029. So this guy will give you 3 cents more than the other guy on 1,000. Again, doesn't look like a big deal now, but which we'll get into that even more later on. This one is effectively that, and this one is effectively that. So you're investing money, right? Which means you want your money to grow as much as possible. So which one is really the best here?
The bottom one.
The bottom one, this one, best, right? If you were borrowing money, it would be almost the opposite, right? The top one would be the best to borrow against. To invest, that one is the best, right? Now, you might see compounded continuously there and say, oh my God, they're going to compound my money an infinite number of times per year. So you might be tempted to go with the third guy. But if that doesn't fool you, you might see, 3.97% versus 3.96%. The 3.97 is higher. Yeah, but it makes a difference when you're compounding 4 times per year as opposed to 365 times per year. At the end of the day, that guy comes out the best. So APY, we can make the comparison quite easily. We can see and just compare the numbers by visual, right? Whereas with APR, you can't always do that. Yeah, so that's why APY is useful. Let's actually talk about what I want to do now.
Mr. Smith, what does APY stand for?
Annual percentage yield. I wrote that earlier. Here. Annual percentage yield. Oh, there's one. I'll just mention a few more things because I don't think we have time to start the other section. So I'll just mention a few more comments here. For compounding continuously, the formula becomes, I'm not going to prove it to you here. APY equals, it's e to the r minus 1. So that's actually the formula I used in this section here. Right, all the other rows, I used the original formula I gave you, this one. But notice that this formula has n in it, right? So you can't plug in infinity if there's actually infinite, if n is infinite. So, but you can prove that for the compounding continuously situation, that is the APY formula. And I'll just mention some other things, just a couple things to note. So I'm sure some of you have seen APY before, and maybe you didn't notice the difference between APR or whatever. So I'm just going to tell you some of the places where you would see one versus the other. And so you can kind of know why they do one versus the other. So one thing you should note is that lenders typically advertise APR. While borrowers or investment firms typically advertise APY. And I want you to like go over your statements, your bills and stuff, and actually start to notice this. Notice that on your credit card, they tell you APR, but on your savings account, they tell you APY, right? Now, why would they do that? Well, the APY is going to be higher. So if you're borrowing money from someone, they want to give you the impression that it's a low interest rate. So they're going to tell you APR because that would be like telling you 9.5, right? However, if someone wants you to invest your money with them, they're not going to tell you the APR because that's going to be like, oh, you'll get 9.5 with me. They would instead tell you the APY. They're going to say, if you invest with me, I'll give you 9.8, right? So you'll see 9.5 APR in one context and 9.5 and 9.8 APY in another context. And it just depends on the goal of the person that's quoting you the number. If they're trying to lend you money, they'll tell you APR. If they're trying to get you to give them your money to like invest it on your behalf, they are going to tell you APY. And you can start to notice that, right? Car loans, everything, credit cards, personal loans, they're all going to quote you APR. Investment firms, savings accounts, CDs, all that stuff, you'll notice that they say APY. Start to actually notice that now. Go around and look at these things. Every time you see an ad for like a loan versus a savings account, notice. You'll start to see it now of people telling you APR versus APY. And the reason is compounding is just a nominal interest rate. The name is only a name. Effectively, what's happening to you is something else, and that thing is the APY. And so that's why APY is important. So I would encourage you to start taking notice now. Just look at your credit card bill and your savings account bill and see what they're telling you. We're going to wrap up there. Hopefully that was instructive. We're going to do something really cool next time. We're actually going to start to model repeated payments because so far you may have noticed that we're not really doing anything after that initial investment, right? So we put in $1,000 and we literally forget it for 5 years. No one does that, right? Usually someone tries to repeatedly put in some money, you know, like I'm going to invest $1,000 every month with you or something like that. We're going to look at that situation, how to deal with repeated payments. And we're going to go back to high school and use what we know about geometric series to actually figure that out. But for now, we'll stop there. Unless there are any last minute questions, we can go. Yeah, Peter.
I haven't been able to find the homework. Is it on Gradescope or Jupyter or the syllabus? Or...
It's on the MyMATLAB. So it's neither. So if you go, let's see here. Let me share my other screen with you. Okay, so if you go to the class website, either the syllabus or whatever, you'll see online homework right here. So you do the online homework here. So these are the instructions to enroll. You're going to need this course ID. And once you actually do that, online homework is done here. You click that link and it's going to take you to a Pearson website where you log in and you should see the homework there.
Okay, thank you for that.
Okay. Yeah. So just go to the class website.
I have a question about that. So I saw there was like a bunch of assignments, but there wasn't like no like due date or anything. So which ones do we have to do?
There should be due dates, but I'll make sure that they're visible. But like I said, for the homework, here's how it's going to work. There are two major due dates. So all the homework that you would need for the topics on test one, they're all due the week before test one, right? And then all remaining homework are due the week before test two. So you don't have deadlines like week to week. I gave you the flexibility to, if things get crazy, you can put it off a little bit, and then you can just make sure you do everything by test one comes up. And that being said, I mentioned I do not encourage you to just put it off completely and try to get everything done the week before test one. You don't want to be in that situation. So try your best to do the homework to keep up to where we are. So right now we've covered sections 3.1 and 3.2. So I would recommend doing the homework for simple interest, compound and continuously interest already. The next homework is going to be on future value of annuities and present value of annuities. You don't have to do those yet, but I would try to keep up with the homework. But technically, they're not due for a while. They're going to be due around midterms and then due around the last week of class. But try to keep up, I would say.
So the homework start from
Chapter three. Yeah, there's no chapter two. Chapter two, you need to be able to do some of the calculations in chapter three. That's why I went over it.
Okay. What about the text 1 and text 2? Do we need to finish it?
Text one, what is that?
Yes. Yes, I see your message on the grade scope says text 1 and text 2.
Oh, yeah, grade scope is where you do the tests.
Oh, okay, okay.
So that's not now. The date of the date for the test, if you go to syllabus, and you scroll down, where are we? Yeah, so the date for the test is that March 14th. So all your homeworks for all these sections up to 7.4 is going to be due like the week before that, March 14th. And then on March 14th, you go to Gradescope for the test, right? So the test is on the Gradescope platform. And then the second test is on May 5th. And then all remaining homework is going to be due like the week before that. And so for homework, you go here, you go to Pearson. For tests, you go here to Gradescope. So that's a different platform that allows me to type my own questions, and you'll see. So these are all the classes. You guys will just see your class, which is this one. So when it comes time to it, you're going to see like test one pop up here, and then you're going to click that and go into it. Yeah. So Jupyter is just for your grades. It's like your report card, which you can access here. You can access everything from the class webpage. Syllabus is here. The lecture videos, the recordings of this guy, as well as the notes, is here. You'll see the entire playlist. So right now, you see we have up to lecture 4. When you click on one of these videos, the notes are posted in the description right here. So if you click on that, you'll see a PDF of the notes that I had for that class. All right, so all the notes are there. So that's where you find everything. If you go to class website, you can find everything from there. You can use the class website as like the central hub and figure everything else out.
On my lab math, like the homework, it'll say like module like 3 pre-homework, post-homework. Is that what we're supposed to do?
Yeah, I mean, I didn't set up the homework. What the people who set it up intended for you to do was they wanted you to do some problems before class and then try to redo some other ones after class and things like that. So that's what the pre-homework and post-homework thing is about. So it's about the students, they expected you to go ahead of time, try some problems first, then go to class, then do homework after.
So
but
do all of those, or?
Yeah, you have to do everything, but I give you the flexibility of being able to do it anytime before. Yeah. So all the classes have to do all those homework. So you guys have to do them. I just decided to give you a little bit of flexibility in it. Yeah, but everything you see there should be done.
I have a question.
Yes.
Did you receive my email about the Pearson MyLab? Because I had a little difficulty like how to shade a part of the graph, because it would shade half of it and not a tiny part of it. Like I emailed you. I don't know if you got it.
If I didn't respond, then I probably didn't see it. So maybe
okay.
email me again.
Okay, got it.
But I have another class starting now, so I have to go.
Okay.
But just email me with any more questions.
Got it.
All right,
Bye.
that's it. I'll see you guys in the next one.